Okay. Let's take a sip of tea while I'm waiting for the stream to catch up with me. Ooh. All right. So that is Twitch, and YouTube is presumably happening soon, and there's YouTube. All right. Hello, good morning. We are going to be starting a new paper today, and we took a vote. So the options were Mix Up, which is an ICLR paper, one on compositional semantics datasets paper, and then also datasets and evaluation, and then also this generative modeling with sparse transformers paper. And the sparse transformers paper really won by a landslide. So the voting was on our YouTube and then also on my Twitter. So this is what we're reading. And this was also an option for the last paper, and I was kind of surprised we didn't pick it because there was a lot of chatter around it. And it is also not just an NLP paper, so they are going to be doing a lot of validation on images and videos in particular. All right, hello everybody. And this paper, like the GPT-2 paper, hasn't been published as far as I can find. I did some digging. I tried to see if I could find maybe some venue that it had been accepted to, and I couldn't. So it looks like it's just sort of been published, but not in the peer-reviewed sense, as this blog post. The code is available, so we might check this out on GitHub, and then also the paper itself is on Archive. And like the GPT-2 paper, this is a project from OpenAI, which is I believe it's a nonprofit. It was definitely founded by some people who made large donations to encourage AI and machine learning research. And my sort of impression so far is that the NLP work is, NLP is not the main field that this research group is working in, so that might be part of the reason, but the sort of general machine learning research has been pretty interesting. So this is more of a machine learning paper and less of a specifically NLP paper, so I've got high hopes. All right, so let's dive in. Now that we've got a little bit of background. The paper is by Ryuan Child, Scott Gray, Alec Radford, and Ilya Sutskever, and there's a footnote here, but I was looking and I can't actually find the footnote. I'm assuming it just is that their affiliation is with OpenAI, but there's no actual footnote associated with that footnote marker, so maybe something they'd want to fix. Oop, sorry, I made it big. Get it back down to size. Maybe something they'd want to fix before submitting the paper. Assuming they weren't submitting it to a conference that had anonymous submissions. All right, abstract. Transformers are powerful sequence models, let me zoom in a little bit, but require time and memory that grows quadratically with sequence length. In this paper, we introduce sparse factorizations of the attention matrix, which reduce this to n square root of n. We also introduce a variation on architecture and initialization to train deeper neural networks. It doesn't say neural, just deeper networks. The recomputation of attention matrices to save memory, and fast attention kernels for training. We call networks with these changes sparse transformers and show that you can model sequences tens of thousands of timestamps long using hundreds of layers. We use the same architecture to model images, audio, and text from raw bytes, setting a new state-of-the-art for density model of NWIC 8. That might be a typo. I think it's supposed to be NWiki, CFAR10, and ImageNet 64. We generate unconditional samples that demonstrate global coherence and great diversity, showing it is possible in principle to use self-attention to model sequences of length 1 million or more. All right, so to break that down a little bit, so transformers or fully attentive networks, which we've talked about quite a bit, can model sequences, and then they're saying that as the sequence gets longer, the time to train the model and the memory required to store the model grows quadratically. So if I have a sequence that's 2 items long, I need 4 units. If I have a sequence that's 10 items long, I need 100 units. If I have a sequence that's 100 items long, I need 100,000 units. I shouldn't be doing arithmetic in my head. And they're saying that they have made some architecture changes that have resulted in reducing that from quadratic time to n square root of n. So a sequence that was too long would require 2 times 1, like 2.8 units rather than 4. 10 would require, let's say 9, to make my life easier, would require 27 rather than 81 units, and so on. So it scales much better is the main contribution here, in terms of both training time and memory. So that's useful, especially if you're trying to do stuff. I mean, obviously we want to train our models quicker, right? But also if you want to do something embedded, or something where you have a lot of memory constraints, being able to really pare that down is really nice. And the changes that they make to create that are a variation on architecture and initialization. Presumably they'll talk about that in depth. Recomputation of attention matrices to save memory. So maybe representing them as sparse matrices, potentially, and fast attention kernels for training. And presumably they will also talk about what makes them fast. And then with these changes, they do a good job and get state of the art and do things fast and good, which is sort of the usual claim of any machine learning paper. All right. Oh, hey. So let's read the background. Estimating complex high-dimensional data distributions is a central problem in unsupervised learning, as many downstream applications of interest involve generation of text, images, audio, and other data. Additionally, it is believed to be a key component of unsupervised representation learning. Hello. Recently, neural autoregressive models have shown impressive results in this domain, achieving state-of-the-art in modeling natural language, Josephowicz Fawis. Oh, that looks like Polish. Radford and Dye. Did we read the Radford paper? We might have read the Radford paper. Raw audio, Vendenord and Mehri, and images. I'm not going to read all these citations. So they're saying that autoregressive models. I'm not entirely sure what would make something autoregressive. Oh, that's what they talk about in the next paragraph. And so this sort of general approach is working on text data, audio data, and also images. The methods decompose a joint probability distribution into a product of conditional ones. Modeling these conditional distributions is extremely challenging, however, as they contain many complex long-range dependencies and require a suitably expressive model architecture to learn them. Okay, so instead of saying we know the probability of A and B occurring together, we say that we know the probability of A given B and the probability of B given A. And that is a hard problem because A and B may be, let's say, very far away from each other, especially in terms of text. And you need a very flexible architecture in order to sort of trace that shape, not define, but approximate that function. Architectures based off of CNNs have made great progress in this direction, but require significant depth to expand their receptive field, so you need a really deep model. To address this, WaveNet introduced dilated convolutions, which allowed the network to model long-range dependencies in a logarithmic number of layers. Okay, so WaveNet was a audio generation paper that had like really impressive results. If you haven't listened to some of the audio samples, you should go check those out. And I remember that came out while I was in grad school, and everyone was like, "Oh, wow, this is really good." It's used for a lot of like speech synthesis and voice generation. So like if you want an assistant to speak using a specific type of voice, people are using that particular architecture to do that. I'm not entirely sure what a dilated convolution is. Presumably that's in the paper. And then instead of having a quadratic relationship, there's a logarithmic relationship. So it's still, increases exponentially, but it's a little bit better. Separately, the transformer, Vaswani et al., which we have read, has been shown to excel on many natural language tasks, like 5, which may be in part due to its ability to model arbitrary dependencies in a constant number of layers. As each self-attention layer has a global receptive field, the network can allocate representational capacity to the input regions for which it is most useful. Thus, the architecture may be more flexible at generating diverse data types than networks with fixed connectivity patterns. Aditya says dilated convolutions are timestamp-based convolutions, which are spread out over time. Oh, interesting. So instead of sort of looking at the whole sequence, you're taking a number of convolutions that are sliding. Ryan says, we looked at dilated convolutions a while ago. It's the ones that telescope down. Okay, I vaguely remember that. Well, that was just a mess all around. Spilled tea on myself and lost my, whatever these are called, earbuds. Okay. And we can go check those out if they become super relevant to the rest of the paper. And then the thing that they're saying about transformers is that you don't need, the size of the model doesn't vary based on the length of the sequence. And this is achieved by different parts of the model paying attention to different parts of the sequence. So you can sort of use the same size model, and then when you're looking at different things, different parts of the model are relevant. However, the memory and computational requirements of such networks grow quadratically with sequence length, which excludes their use on long sequences. The main contribution of this work is to introduce several sparse factorizations of the attention matrix, which scale as O(n) log n, with the sequence length without sacrificing performance. These work by separating the full attention computation into several faster attention operations, which, when combined, can approximate the dense attention operation. We use this to apply self-attention to sequences of unprecedented length. Okay, so rather than doing attention over everything, we're doing smaller attention operations and then concatenating them, doing some sort of transformation of them, projecting all of those outputs into a single matrix. I don't know, we'll get to that. Additionally, we introduce several other changes to the transformer, including a restructured residual block and weight initialization to improve training of very deep networks. So changing how your network starts. I don't remember what residual block is. Presumably we'll get there. A set of sparse attention kernels, which efficiently compute subsets of the attention matrix, and recomputation of attention weights during the backwards pass to reduce memory usage. Oh, interesting. So you recompute both in the forwards and the backwards pass? Interesting. We empirically validate that models augmented in this manner can achieve state-of-the-art compression and generation of natural language, raw audio, and natural images. The simplicity of the architecture leads us to believe it may be useful for many problems of interest. And Ryan says, probably not important, but the diagram for WaveNet, which I'm assuming is not being shown because it's a link. Let me see if I can get there on my phone real quick to approve it. If not, I'll do it later. Should not be a problem. There we go. Show. So there's a link in the chat to the diagram for WaveNet that you guys can check out with the dilated convolutions. All right. Related work. The most related work involves other techniques for scaling up autoregressive generative models. Hi. For images, read it all 2017, models conditional independence between the pixels in order to generate many locations in parallel, and imposes an ordering and multi-scaled upsampling procedure to generate high-fidelity samples. There's something wrong with that sentence. I think it doesn't have a verb. Let's just say for images, models model conditional independence between the pixels. Conditional independence between the pixels. I understand all those words separately. I don't really get how that's going to affect your image generation, but again, if it's relevant to the rest of the paper, we'll get there. Imposing an ordering and multi-scale upsampling procedure to generate high-fidelity samples. Multi-scale upsampling. Interesting. So generating images that are bigger than the input images, and I'm guessing interpolating between the missing pixels. Idea says it's with reference to paper, the paper models. Oh, I see, the paper models. Gotcha. Oh, the author name should be outside of the parentheses. Gotcha. So saying that the authors modeled that. Parmar uses blocks of local attention to apply transformers to images. So I'm guessing that's sort of like, rather than being, a vector, it's a matrix and maybe sliding over the image like a convolution would. I'm just guessing. I don't know for sure, but that's what I'm getting from that description. For text, Dai et al. Introduces a state reuse memory for modeling long-term dependencies. Oh, okay. And for audio, in addition to Van den Oord, Mary uses hierarchical structures and RNNs of varying clock rates to use long context during inference, similar to other papers. So instead of just sort of having a flat structure, using a hierarchical structure and RNNs, which there is some evidence that RNNs in particular are better at capturing hierarchical structures than transformers. And then Huang et al. Applies transformers to MIDI generation with an efficient relative attention. So it looks like there's a lot of different ways of applying attention, and then this paper is proposing a new one. Our work is simpler than many of the techniques above and can be applied equally across images, text, and audio. Many of the above techniques are orthogonal to ours, moreover, and can be used in conjunction with ours. So they're saying that the changes that they make are separate, and you can make those changes and also the ones that they're proposing in this paper. So you could do ensembling, or you could have one model that applies multiple of these techniques. Outside of generative modeling, there are several works relevant to improving the efficiency of attention-based off-chunking. Off-chunking? Or using fixed length representations. Oh, attention based off chunking. So you do chunking of the text beforehand, and then your attention is based on that. Or using fixed length representations. So instead of, having variable lengths, which again, longer sequences require bigger models and longer training time, using a fixed length, which imposes some stricter assumptions, but might be more computationally efficient. Other works have investigated attention with multiple hops, such as Sukhabatar, I know there's a vowel distinction there that I'm not saying right. And Gehring. So that sort of sounds like skipgrams to me. If you are doing n-gram-based language modeling instead of transformer or neural-based language modeling. It is worth noting that gated pixel CNN and WaveNet use multiplicative interactions in their networks, which are related to self-attention. Okay, so these earlier architectures, which came out before the attention paper, are doing something like attention, but not quite the same, or something like self-attention, but not quite the same. So there's a lot of people that have done sort of like similar work and are exploring the same space, but haven't actually done the exact same thing that these authors are proposing. Also, they just never referred to figure 1 as far as I can tell, so let's go back up and look at figure 1. These are definitely generated images because they look like nightmares. Unconditional samples from our neural autoregressive model on ImageNet64 and a classical music dataset. So here is the classical music, presumably, and you can see that there's sort of rhythmic structure. There looks to be some maybe, I don't know what would cause this. Maybe this is the whole orchestra together, but I don't know why that would be quieter. So distance from the midline is intensity. And then here we have, I don't know, sort of a very structured piece of music. We use the same self-attention based architecture for audio, images, and text, although they don't have any text examples here, which is sort of interesting. The samples above were generated with soft max temperature 1 and had lengths 12,288 and 65,536. Audio samples can be listened to at the blog post. So which is here, and I don't believe you get my system noise, so if I play this you won't actually hear it, but if you guys wanted to go through and check out the audio samples, you could do that. Okay, so that is the introduction and the related work, and we're going to move on to the background, and we're going to slow way down here. We consider the task of autoregressive sequence generation, where the joint probability of a sequence x equals x sub 1 through x sub n is modeled as the product of conditional probability distributions and parameterized by a network theta. So the probability of x is, I definitely know what this is. I think this is the sum of the conditional probabilities. What's that? Big pi, sum probability. Sigma and pi notation. So that's the product instead of the sum. As Aditya has just mentioned. Thank you. So we take the product of the probability of x sub I given x sub 1 through x sub 1 minus I and theta. So we are looking at the probability of each item I. So I'm guessing this is our vocabulary, maybe? And we are looking at the probability of the next, let's say if we're working with text, we're looking at the probability of the next item in our sequence, given everything else that came before it in the sequence, and also theta, which is our network weights, I'm assuming. So we are taking the product of the probabilities of sequence X. So that's the probability of the sequence, and then we can compare multiple sequences and find which one is most probable. And Leonardo says, product of conditional probabilities. Yes, thank you. We treat images, text, and audio as a sequence of discrete tokens, typically raw bytes. The network theta takes in the sequence of tokens and outputs a categorical distribution over the v possible values of the next token using the softmax function, where v is the size of the vocabulary. Okay, so v actually isn't in this, so the vocabulary isn't actually in this equation. It's in the network itself. The training objective is to maximize the log probability of the data with respect to theta. So we want our network theta to say that things that are likely given the training data are very likely, and things that are rare given the training data are very rare. And so I'm guessing that this is just sort of the... there we go. I don't know why it started to cut off the top of some of those letters in the PDF. So this is the probability of the final sequence, and the thing that we are training is this network that is giving us the softmax over all of our possible vocabulary items. And then we're also using information about which items came earlier in the sequence. A simple and powerful choice for the model theta is a transformer, which we read about earlier, in decoder-only mode, as demonstrated by Radford and Liu. We've definitely read both of these papers. So the transformer was proposed as a machine learning model or a sequence-to-sequence model with an encoder and a decoder. And if you take the decoder only, I thought it was encoder only. Am I making that up? I'm pretty sure it was encoder only because we read that last, and not using the decoder for generation. Okay, so you use the decoder for generation and the encoder for things like language modeling. Did Radford and Liu do language? They were doing language modeling, right? They weren't actually doing generation. JRC says, Fernandez says, what is the name of the paper? The name of the paper is Generating Long Sequences with Sparse Attention. And I will paste the link as well. What? Jer says, does this model count as language modeling? So I guess you would say that the network theta is doing language modeling, but the task here is generation rather than language modeling. Okay, I'll go and check that at some point, whether or not it's the agreeder. Leonardo says, I agree encoders for language model and decoders for language generation. I think that's just a typo. I think that Radford and the Liu papers both just used the encoder and not the decoder. These models transform the input sequence with blocks of multi-head self-attention over the entire sequence, followed by dense transformations over each sequence element. The self-attention portion of the network must compute n weightings for each of the n elements, however, which can quickly become intractable as the sequence length grows. Okay. Transform the input sequence with blocks of multi-head self-attention, so that's what's proposed in the Vaswani paper, over the entire sequence. So you're looking at everything, followed by dense transformation over each sequence element. So looking at each... Excuse me. So looking at each element individually. The self-attention portion of the network must compute n weightings for each of the n elements, however, because it's looking at the whole sequence. So as the sequence gets longer, the size of the network needs to get bigger as well. Robbie says good night. Good night. In the following sections, thank you. In the following sections, we describe our modifications to the transformer architecture, which make it more suitable for modeling long sequences. So they're saying that it works really well for very short sequences, which makes sense. I'd say the majority of machine learning, the majority of machine translation tasks tend to be more sentence-based. I mean, it's rare for me to use machine translation to translate a very long text. I don't know if you guys do the same thing, but generally I'm up to maybe 400 words at a time. Mostly I use it to translate the Japanese language Kaggle Slack, so I can see if there's any questions for me. And that's not super great for very long sequences. Although it's interesting that they're focusing on generation here, particularly because the evaluation for generation, especially text generation, is pretty much, there aren't standard practices in the field yet, and that might change. I know there's going to be a lot of work on that at NACL coming up in a couple weeks, but it's a little bit hard to evaluate, whereas things like language models, we have perplexity to evaluate, we have mostly perplexity. But I think the image generation evaluation is a little bit better, and this seems to be a research group that's more focused on computer vision than NLP, so I'm assuming that they will do good evaluation at the end. All right, factorized self-attention. Sparse transformers separate the fully self-attention operation across several steps of attention, as visualized in Figure 3b and 3c. To motivate our approach, we first perform a qualitative assessment of attention patterns learned by a standard transformer on an image dataset. So here's Figure 3. When did Figure 2 come up? Did you guys see a reference to Figure 2 I just missed? I guess we'll just look at Figure 2 here. Figure 2, learned attention patterns from a 128 layer network on CFAR10 trained with full attention. White highlights denote attention weights for a head while generating a given pixel, and black denotes the autoregressive mask. So if you remember from Transformers, you don't want to look into the future when you're generating things. The decoder, specifically not the encoder, has a mask for upcoming things. Layers are able to learn a variety of specialized sparse structures, which may explain their ability to adapt to different domains. Many early layers in the network learn locally connected patterns, which resemble convolution. In layers 19 and 20, the network learns to split attention across a row attention and column attention, effectively factorizing the global attention calculation. So that is what's shown in B. So starting with A, so if we look at attention, which is the white pixels, you can see that it's looking at the things directly before the mask, which is similar to convolution, where you're sort of sliding a smaller square over a bigger square. In B, they're saying column attention and row attention, so we can see that attention is looking at along sort of the X and the Y axis. C, several attention layers show global data-dependent access patterns. So here we can see it sort of tracing the back of this bird. It's focusing on the face of the dog here, focusing on the highlights on the dog here. So they're suggesting that it's able to sort of do it's able not just to focus on things based on the current place in the pixel generation, but also on the content of the image. And then D, typical layers in layers 64 to 128 exhibit high sparsity, with positions activating rarely and only for specific input patterns. So if we look here, there's almost no white pixels. Here, it looks like this one in the corner is white, maybe? Interesting. So it looks like it's focusing. Actually, that might be from the way the image has been cropped. So here, it looks like there's only attention directly in front of this car down here. Here, I don't see any. I don't see any. So they're suggesting that as you go, so the very low layers of the network are sort of acting like convolutions. Moving up, we see column and row attention. Moving up, we see attention focusing on the structure of objects in the image, and then finally it sort of peters out. Only for specific input patterns. So it's sort of looking at very specific things that are relevant to the pixel it's generating, hopefully. Interesting. I still don't know where they were talking about figure 2. And then figure 3, so the so figure A here is the transformer originally proposed attention structure, and then figures B and C are the ones that are proposed here. So two 2D factorized attention schemes we probably were evaluated in comparison to the full attention of a standard transformer. So in a transformer, as you're going along, you pay attention to everything before you. I don't know what the difference between this and this is. I'm guessing that this might be, because if you remember in Transformers, you learn the values and the keys. So I'm guessing that this might be the value and this might be the key, maybe. And instead of learning those values for the whole matrix, and again, this would be just the decoder, the encoder would look at all of the sequence, the whole thing, as opposed to masking it, which we see in the decoder. And maybe that's what we're seeing here. So so this must be stepping through time. All right, let's continue reading and see what they say. The top row indicates, for example, 6x6 image, which positions 2 attention heads, which positions 2 attention heads receive as input when computing a given output. Okay, so when we're computing an output here, we're paying attention to both of these things. Oh, it's multi-headed attention. So this is head 1 and this is head 2. Gotcha. That makes sense. The bottom row shows the connectivity matrix, not to scale, between all such outputs, rows, and inputs, columns. So these, I see. So this is the output, this is the input, and then, so this is time. As we are stepping through our image, we're looking at everything that's come before, or through our text or whatever. Okay. Sparsity in the connectivity matrix can lead to significantly faster computation. That makes sense because you don't have to compute all of these squares, you can compute only some of them. Excuse me. In B and C, full connectivity between elements is preserved when the 2 heads are computed sequentially. We tested whether such factorizations could match in performance the rich connectivity patterns of figure 2. Figure 2. 128 layer with full attention. Okay, so this is a transformer, so a fully attentive network, and they're interested to see whether they get the same sort of pattern when they don't look at the whole previous part of the image every time. So here here it looks like head 1 is looking at just the very previous pixels, so this would be like an n-gram, the last 6 words, and head 2 is sort of skipping back. So that would be a skip-gram that skips every 6 words over time. So at each time point, we are always looking at the immediate last words directly before the one that we're generating, or pixels, but we're also using this sort of skip-gram type of attention to sort of sample from previous words or pixels. So this is strided, so we're sort of sliding it along. And then there's also this one where, so this look only really makes sense for images, where as we're moving through the image, we only look to the border. So instead of maybe wrapping around like this one, we start here, 2, 3, 4, 5, 6, and then on the next row, 2, 3, 4, 5, 6, ignoring everything in the previous row. And then this, we're only looking at one of the columns. So as this moves, this doesn't move. So as the tension moves across, we get to the point where we have sort of a square in the image, or rather a right angle. Is what I'm picking up. Okay, my intuition is that for text, this sort of sparse model, the strided model, would work better than the fixed model. But that, again, is just my intuition. Because you would be, at some points, generating a word, only looking at the immediate previous word, and then a word 6 words ago, which I don't think is going to be as effective as always looking at the previous 4 words, which is sort of the idea of an n-gram. And we used those for years, and they worked great. Okay, so that's the difference. Is that okay? Excellent. I was like, is that all of the description we're getting? We're not getting the same information as a formula. Woo. I should have had coffee instead of tea. All right, qualitative assessment of learned attention patterns. We visualize the patterns. Oh, here's figure 2. We visualize the attention. Why is figure 2 after figure 3 in the text? Oh, okay, that's super duper frustrating. Figure 3 should be after figure 2 in text references. Your figures should always be ordered by when you refer to them in the text. We visualize the attention patterns learned by a 128-layer self-attention network on CFAR 10, which is an image data set. That sounds right to me, and present several examples in figure 2. Visual inspection shows that most layers had sparse attention patterns across most data points, suggesting that some form of sparsity could be introduced without significantly affecting performance. Several layers, figure 2c, clearly exhibited global patterns, however, and others exhibited data-dependent sparsity, figure 2d, both of which would be impacted by introducing a predetermined sparsity pattern into all of the attention matrices. Oh, gotcha. So what they're saying is it's really hard, so it's really easy to capture this pattern of attention using a sparse network. It's much harder to capture this pattern of attention and like this pattern of attention where it's only looking at one pixel that's pretty far away using a sparsity network, a sparse network. In this paper, we restricted our investigation to a class of sparse attention patterns that have connectivity between all position over several steps of attention. These methods can be more efficient than full attention while still providing global context to any given position. We aim to empirically validate the performance of these factorized patterns on a range of tasks, given that they are unable to learn the exact same mappings as those in figure 2. Which makes sense, because if you've forgotten, you aren't doing attention over the whole image, something like this is going to be pretty hard to do. We present the formulation of factorized attention below. All right, math time. Factorized self-attention. A self-attention layer maps a matrix of input embeddings X to an output matrix and is parameterized by connectivity pattern of S equals S1 through Sn, where Si denotes the set of indices of the input vector to which the ith output vector attends. So S here would be all of the blue squares, the lighter blue squares that a particular output, the dark blue here, attends to. The output vector is a weighted sum of transformations of the input vector. So the attention on X, the matrix of input embedding, so those would be pre-trained, to the pattern is... Actually, let's read these bottom to top, because I think that makes more sense, because it's sort of nested. So this here is this, and this is this, and then this is this. Okay. So this term, KT sub S sub I, so for K, which I believe was the notation for the key. Yeah. So remember the keys, values, and queries are all learned. This isn't something that you're specifying ahead of time. So K here is the key for the jth item in X, where J is the set of SI. Oh, what's the weird E mean? I think it means we're looking at the whole set. Does that sound right? So we're definitely looking at SI here. We're looking at SI here. This one's the value, this one's the key, this one's the query. So we're only looking at the query for the ith item. J in SI. Okay, where J is in this set of cells, pixels, words that we're attending to. Yuri says weird E belongs to. Leonardo says one of or in. Thank you, that's helpful. I did take set notation in grad school, and it was a minute ago. Okay, so we've got our values, we've got our keys. Where did D come from? Where did D come from? Is it defined up here? I don't see it. All right, so we've got our key for our items multiplied by our, so the term for our query for our items multiplied by the key by our items divided by the square root of D. So we're going over all of the possible X's in our set. We're dividing by the square root of D. Again, I do not know where D comes from. Maybe we'll come across it in the future. That might just be a term you define, I guess. Oh, Giri says D is defined later in the paper. Thank you, helpful. Just like computer programs where you can reference a variable before it's defined, right? Sorry, I'm very snarky about mathematical notation. I don't think it's a great way of conveying information now that you can just give people code. And the value, and then we're taking softmax, so we're looking we're looking at the probability we're distributing attention as a probability over each of the items that we're looking at in our sequence beforehand. Giri says D is the inner dimension of the queries and keys. Oh, okay, so it's just like how big did you decide to make the queries or the keys? And then we do that for every item in our which transform a given xi. So that must be an item in our vocabulary, I guess. Let's keep reading the rest of this and see if that helps us figure it out. So here WK, Q, WK, and WV represent the weight matrices, which transform a given xi into a query, key, or value. Oh, and D is the inner dimension of queries and keys. I just can't read. It was literally right there. The output at each position is a sum of the values weighted by the scaled dot product similarity of the keys and queries. So that's like what we read in the Vaswani paper. And the big difference here is that we are looking at just some of the items as opposed to all of the items that came before the current item. Fully self-attention for autoregressive models defines SI as J less than I, allowing for every element to attend all previous positions and its own positions, which is what I just said, but in fancier math words. Excuse me. Sorry, I'm still sniffy. Factorized self-attention instead has P separate attention heads, where the mth head defines a subset of the indices and lets SI equal AIM. Okay, so they're saying that instead of attending to everything, we're only attending a subset of the indices. And we want to choose the best subset where AI is equivalent or proportional to, I do remember this, the square root of n, where n is, presumably we'll get to it, probably number of items in the sequence, or length of the sequence. Additionally, for the time being, we consider valid choices of A, where all input positions are connected to all future output positions across P steps of attention. All input positions are connected to all future output positions across P steps of attention. For every j less than I pair, we set every A such that I can attend to j through a path of locations with a maximum length of p plus 1. Specifically, if j, a, b, c, I is the path of indices, then j is one of A1, A is one of A2, B is one of A3, and so forth. We set each A such that I can attend through J through a path of locations. Okay, so I think what they're saying here is that if I'm at this one, by moving backwards through attention, so if I look at this one, or like 4 back, and I come here, that will give me, and I continue that process, I can attend to everything. It just takes more steps instead of attending to everything right away, if that makes sense. So I think what they're saying is that they don't want to do something such that like there's a gap here, so that this, if we're looking at a specific output, none of the inputs have not previously not been outputs, so that they can sort of like move back through the entire sequence. So they wouldn't do something where like 1, 2, 3, 4, and then they skip to, so like if you removed these 2 rows and this column, there'd be a disconnect here, so you'd look back with your attention, and then it would just sort of end here, and there would be no way to figure out what attention this particular item gave to previous items, I think is what they're saying. These 2 criteria allow us to keep the ability of transformers to propagate signals from arbitrary input positions to arbitrary output positions in a constant number of steps, while reducing the total effective computation to O of n square root of n. We also note that softening the validity criterion, for instance having a series of only locally connected layers, may be useful inductive bias for certain domains. So prioritizing more local items might be better. And I can definitely see that, especially for like language generation and modeling. Arbitrary input position to arbitrary output position in a constant number of steps. Oh, I see. And the shape that they pick should be such that we can always go like 3 steps to get back, 6 items or whatever. In this work, we explore 2 factorizations for p equals 2, which we describe in the following section, though we note that the same techniques can easily be extended to higher dimensions. Okay, so they're only working in 2 dimensions. They're saying that you could work, this could work equally well in higher dimensions. Okay, that's making sense to me so far. Um, So the big thing here is that instead of attending to everything, we're only attending to some things, which is what makes it sparse. We can still sort of like walk back through our sequence and look at the attention at each layer of, at each output to get the attention for previous inputs. But if we don't need them all the time, we don't need to hold them in memory. So for things like this, where we're only going to be attending to a single pixel or like 2 pixels at this stage, we can still get there by sort of like walking back through our sequence generation and looking at attention in previous outputs. But we don't need to have the whole picture in, or the whole set in memory. Well, I guess it's in memory, but we don't need to have it like accessible and calculated at every given time because most of the pixels we're ignoring, I think is the argument that they're making. And I don't think we can get through the next section in 5 minutes. So I think I'm going to wrap up the reading here. And I actually want to see really quick, just for my own curiosity, if they have some examples of generating text. So here are some generated images. And again, nightmare fuel. Here are the audio samples, which I think if I play, you won't be able to hear, unfortunately. Wait. They said they did text. Ain't none. They don't have any text examples. Do they have any text examples here? Compression, in wiki, dense attention, sparse attention, increased speed. There's no samples of text generation. Is this the same group that released GPT-2, where like the entire press release was just samples of text generation? Do they have some in the GitHub repo? Attention.py, utils.py, readme.markdown. Yeah, I don't think they have any text generation examples, which I guess it is sort of easier to look at modeled images, but that's also pretty weird. Oh, and then here's an animated example of this attention that we were looking at here. So here's the one where it sort of looks like it's learning row and column attention. Here's the one where it sort of looks like convolutions, and here's the one where it's sort of generated, where attention is based on the quality of the image itself. And then this is what should be hardest for a sparse model to capture. Nicholas says, recently found these videos and enjoyed them, even though a lot of it goes over my head. Please continue the great work. And feel free to ask questions. I'm just sort of figuring it out for myself. And if stuff is confusing for you, I'm perfectly happy to work it out. He says, maybe in section 7.2. CFAR, examples, text, we trained. No, I don't see any examples. And there's no appendix. Noted. Okay, if you guys can find some examples of text generation, I'd be really interested to see them. And we will pick back up next Wednesday. I'm like 80% sure. I'm going to be at a conference next week, but I don't believe it overlaps with this. It's the American Statistical Association Symposium for SDSS data science, I guess. Data science and statistics. There we go. But I'm pretty sure I will be here on both Wednesday and Friday. And also I am going to be switching to 9 a.m. on Friday for live coding, so in the same time slot, just because I think it works for more people. And if that's worse for you, I'm sorry. But it just, looking at like what time zones people are in and when it's reasonable for people to be awake and watching a live stream, I think that's the best time for the most people. So, all right. So when we come back in, we're going to talk about two-dimensional factorized attention. So we sort of like looked at the math for just like the blue ones here, the darker blue and not the lighter blue. And we'll talk about adding the second dimension next week. And we'll pick back up with that. And I'll see you guys then. And I'm trying to think if there's something else I need to say. I think that's it. The Kaggle Days video from San Francisco are up on the channel, so if you're interested in more data science-y sort of video content, there's plenty of that we've added. Otherwise, I will see you guys on Friday. Thank you for joining. Have a great week. And we'll do some live coding on Friday. We'll see you then. Bye.